Okay, let's try to record both of them. So, last time we tried to evaluate this diagram, and this all the alpha, this should be proportional to gamma mu f2 q square delta f2 q square plus sigma mu 2m q nu 1 q square as far as equal I times. Is it the correct one? Yeah, please refer to the latest lecture note. Always.
I'll introduce you need that.
Oh yeah. Thank you very much. Oh, wonderful. Thank you very much. Thank you so much. Yeah, I think 1 and 2 are opposite side. This is 1. And this is 2. Okay. And then last time we do the loop evaluation, applying Feynman diagram, and do the tedious calculation, and we arrived this one. And to do that, in fact, this is renormalized one, so this is, we call it delta 2, delta 1, which is 1 minus d1. No, 1 plus, let's see, minus 1. Sorry, z1 minus 1. So this is what we have. So therefore, what we are interested in the even though if you calculate this loop diagram, you encounter the it used to be this one is a delta lambda. It used to be here. It used to be delta lambda in the numerator here, but if you take the difference, you can just avoid the infinity. So the important thing is that the infinity is just pushed into this delta f1 0. Both have a infinity, but the difference is important. That's what we learned last time. And then we can just push the infinity to the counter term, which is the difference from the UV like a Bayer Lagrangian and then the physical Lagrangian. And this part we cannot measure. So the infinity, so the difference, so the schematic picture is that this is energy level, and then we just integrate over from 0 and whatever q square or whatever k square. So this k and k prime we call it, and then p minus k, and so on. So what we are interested in the difference between delta f to 0 and delta f to q square. Okay? What's happening in high energy, we're not interested in because we cannot measure. So what we're interested in the difference between these two. Then that is the philosophy or technique to that is the notion of the concept of renormalization. So, but we will learn that this is not the technique to avoid infinity. This is indeed the way of understanding physics, the way of understanding. So we are not interested in the high energy because we are not measuring. We're not going to measure. So we are interested in the physics which can be measured. And what's happening, we will learn many things in subsequent lectures that essentially, so, I don't think I have time to introduce path integral this semester. Maybe the beginning of next semester, I will introduce path integral. And then So if you introduce path integral, so we will learn so-called much more sophisticated way of understanding the normalization given by Ken Wilson. Essentially, what we are interested in is the given Lagrange, which is integrated over all the possible degrees of freedom of high energy. And what's end up with we are interested in the difference between them. So that's the later subsequent lecture. So you just probably you guys are tired of doing homework. Probably you spent a long night yesterday. But anyway, so subsequent lecture, you can just look forward to the new concept. But anyway, so that's we alive this. Sorry, not F2. Sorry, F1. I'm just swapping the F1 there. Sorry. So now also here, so we avoid UV divergence by taking difference. But now, as I mentioned last time, it also have IR divergence. So which means mu goes to 0. When mu goes to 0, this integral also diverges. And we will see how to avoid this divergence. Okay, so to do that, so let's call this one is equal to f renorm of Q1 Q squared. Maybe delta, but anyway. So okay, let's go delta. More precisely, delta means order alpha. Order alpha. So delta f renorm 1 Q squared at IR divergence. We're only looking at the mu goes to 0 part. What is the dominant part of the mu goes to 0 part? Then when mu goes to 0 part, this can be this part you can ignore, and then what's relevant part is this part. So what's relevant part is this part, in fact. Let's see. This part. Let me check my lecture note. Sorry, I didn't print out the previous calculation, and then need to check what I'm doing here. Good. Okay, so this is the. I think I should write down Q squared, and then here, in fact, yeah. I mean, okay. Now, before going that, I should write down the expression delta mu. Delta mu Q squared is equal to 1 minus z squared n squared minus q squared 1 minus z minus y y plus mu squared. So this is the sorry. I think I should write down this is xy, just mu squared and z squared. So xy plus mu squared and z. And then this is indeed. So this part is indeed. So when you take a difference, this is indeed difference between this term and this term is just a difference between these. And then if you only look at the when mu square goes to 0, mu square goes to 0 part, I mean here the contribution of mu is, I mean the dominant part becomes like here, and then no, sorry, I think yeah, sorry. So when mu goes to 0 part, if you only look at this one, so they only counter each other, so you get the 1, so you can ignore this part. And what we are interested in this orange part, if you look at the iron divergence, and then we will just rewrite this part is the delta F renom. I mean, just repetition of the IR part is equal to 2 pi dx dy dz delta x plus y plus z minus 1. And then, I mean, just repetition, sorry. I think it makes you bored. Q squared 1 minus x 1 minus y divided by delta mu is this one forward. I think it's not eliminating to write down everything. But anyway, I already did that, so let's finish. Minus okay, now so we're into the mu goes to 0 part, mu squared goes to 0 part. And then what's relevant is that the mu squared xy, so if you look at that, so it's multiplied by z, okay? It's multiplied by z. So therefore, what's important, mu squared goes to 0 is the region xy is around 0 and z is around 1. That's the important part of this integral. When the So therefore, if you take this, if you only look at this region, so this can be written as follows. So I'm not gonna write. So this is the integral alpha over 2 pi, and the integral is the same thing out of the delta function. And then so we just substitute z equal to 1 around here. When z equal to 1, so this will give you, this part will give you minus 2. So z equal to 1 minus 4 plus 1 is minus 2. And the x, if you put the x and the y equals 0, it's just q squared. So therefore, this becomes n squared minus 2 plus q squared. Okay. And denominator, we have to keep track of it because I mean, denominator is an important part. So 1 minus d squared m squared minus q squared xy plus mu squared and z. Good. Mu squared times z. And then I think z is just approximately 1, so just ignore. And then the same, you do the same thing here. So then, so here you get the minus 2 from this factor, and times minus 1, you get the 2 times like this. Okay. Now since we are looking at this region, so this integral can be written. Just perform this integral delta function. There's no dependence of x here now. Oh, there's a dependence of x. But if you perform this x integral, this can be written as follows: dz and 1 minus z 0 dy. And then here, what we have is 1 minus d squared. Maybe I should square and square. Like this way, plus mu square. Okay, so that's what we have. So that from here to here, we just perform x integral. The integral. Okay, and then make change a variable. The following change a variable, we will get the following expression. I think it's better not to repeat the old calculation. And we just do like, sorry, w is equal to 1 minus c. And then, so I will skip one step. Delta F1 we know, q squared. This step is written rational, so I'm not gonna explain the detail. is around minus alpha over 2 pi FIR Q square. I will skip one step because that makes it bored. Divided by mu square plus order, where the FR FIR, what's that? Oh yeah, FIR Q square is equal to 0, 1 m square minus Q square over 2 divided by m square Q square C 1 minus C dC minus C. So I mean from here to here, you just change a variable like this way. So make change of variable here, and then just do some simple integral. Some simple integral, you end up with this one. And in fact, yeah, you end up with. So I'm going to skip so the detail from here to here. From here to here, you just take a look at lecture notes. I think if you do the calculation, it just makes you bored. Okay. Is it okay? Well, do you want me to perform? Is it okay? Okay. I can skip? Okay, good. Okay, so the IR dimensions you can easily see is if you take mu square goes to 0, mu square goes to this part is divergent. That is IR divergent. Okay. And we need to think about how to treat it. Okay. So sorry. There's something wrong about my recording. Anyway, so this is IR divergence. Okay. So to avoid this one, so as I mentioned at the end of the lecture last time, so we need to incorporate the following in the diagram. So this, in fact, the cancel. So as we supposed to cancel the following diagram. This is K. This is like this. So this is the diagram, it's called, as I mentioned last time, it's called RAM. Sorry, I think should go RAM 1. So as I mentioned, so this means it's a German language. This is RAM is a break, and this is radiation. This means radiation. So this means that if you have a nucleus here and then the electron is emit the photons, gamma. Okay. So electron and a nucleon. So if the electron is accelerated, it emits photons, and then it loses energy. So that is called the lose energy. By emitting radiation, the electron is the decelerate. Break means just a break in the car. So So therefore, so this is the Bremsstrahlung. It's called Bremsstrahlung. So which means that the electron, when electron moving, so it emit photons. Okay, photons. But we are interested in that when K is very small. So the K is very small. P minus 2 pi. It's called soft photon. Because the momentum is very small compared to the electrons. And if the momentum is too small, the experimental device cannot detect. Okay? So if K is very small, there is a the limitation of the experimental device whose the minimum, which can detect the photon at the certain energy level. So which I call it E minimum. If K, the absolute value of K is lower than this one, experimental device cannot detect the photon because the energy is too low. But there must be such a procedure. Even though we cannot measure, the photon with the energy lower than this one should occur. So therefore, we should evaluate this one, which we cannot detect, and then evaluate the contribution which we cannot detect. Okay, that's what we are going to do. So we are going to do is that the evaluate this diagram where K, the energy level is lower than this one. So what is the contribution of this diagram? Okay, and if you magically, we will see that if you add them up, if you include the contribution here, in addition to this one, the IR divergence will cancel. That's what we want to see. Okay. So, any question at this moment? Okay. So that's what we are going to do, and then yeah. So in fact, this next homework. Okay, you don't want to listen to about next homework. The last homework. The next one is the last one. So, and I'm wondering the next homework due in 3 weeks. I'm just trying to make it a bit like a deadline, postpone 1 week later, so that you have more time, right? Anyway, but some students are taking a particle physics course, so it doesn't make any difference. But if students who do not take particle physics, it's going to be a bit easier. But anyway, so this integral is important in the next homework, in fact. Anyway, so this cancellation will be just showing cancellation will be homework next in the last homework. So you guys should concentrate on it. Anyway, so let's evaluate this diagram. Okay. So in amplitude it's very simple. I heard the particle physics course is very difficult. So this is the okay. So here is the first diagram. So this is P minus K. This is P minus K, and the gamma zero is indeed this gamma zero upright here. Gamma zero. The P minus K, P prime, P minus K, and the Q here. Gamma zero is here, so it's just 3 levels. And then it's quite amazing that I thought my course is one of the most difficult courses in the Fudan, but Gujan's course is much more difficult than mine. It's quite amazing. Anyway. But in this course I try to anyway easy on you. Just writing a lecture note and then recording lecture and so on, setting office hour. I hope it's going to be okay for you guys. So here this one is so here this should be p prime plus k. So therefore the second diagram is this one. Okay, and now so if you use this approximation, so much less than. So this is an assumption. If you use this assumption, this tree-level amplitude, so the k is very small, so the difference between them is very small. Therefore, we can approximate p prime p minus k, gamma 0, p prime plus k. P is approximate equal to just ordinary p prime and p. And also, if you have the, so this is an approximation. But I think, this kind of the computation is very important in quantum theory. So if you have the propagator like this way, this can be written p plus k, p minus. Like this way, then the k is very small. So therefore we can ignore k. But important thing is to just keep track of in denominator. Denominator of k is very important. So we can ignore k in this soft photon limit, but you have to keep track of the denominator. Denominator is very important. Okay. So so we can go further step. Since this is photon p minus k, p and the k are moment. P is the propagator is the electron, and the k is the photon, momentum photon. So therefore, if you expand this one, p squared is equal to m squared, and k squared is equal to 0. So therefore, this can be understood as p slash plus m 2 times pk, 2 times p dot k. That's it, and the minus sign. I'm sorry, I think you cannot see. So if you expand the denominator, p squared is equal to m squared because of it's a momentum of the electron. And the k squared is equal to 0 because it's a momentum photon. So therefore, the cross term is minus 2p dot k. So therefore, what we have is equal to minus p slash plus m 2p dot k. So that's what we have. Okay. So that's a soft photon approximation. Soft photon approximation. And plug that one into here. And then, so what we have is that so it's going to be a very simple expression, U bar. So therefore, gamma 0 your P E times P prime let's see what I'm doing here. Just a moment. Let's see. Okay, let's write one by one. So, okay, let's write the one by one. Otherwise, you will get lost. So the first one is gamma 0, then P prime and P, and here what you have is minus times I times P slash minus K slash plus M divided by 2 dot P, 2 times P of K, and minus IE gamma mu of P, and it's gamma mu star. Like this way. And the second term is U bar P prime minus IE gamma mu. And then what we have is that the now P slash prime plus K slash plus M divided by 2 dot P prime dot P. Okay, they agree? Yeah, it seems okay. And then U of P and E mu star. Okay. Okay, so that's what it is. I think I missed the gamma 0. I think if I put the gamma 0, I should put the gamma 0 here. Okay. Gamma 0, P prime and P, and U of P, and E mu star K. Good. So that's what we have. Now we need to use the equation of motion. That the so here we apply the equation of motion. So therefore, so here P slash. So this part is indeed equal to 2p mu up. So you just apply Crefeld algebra to get this one. Okay. So I think I told you wrong. Why do I have keep track of K slash? Sorry, I don't need K slash. Sorry. So numerators, as I mentioned, I don't know why I keep track of K slash. So we don't need a K slash. We can ignore. Sorry. My brain is not working. Okay, so this is okay. Good. So this is you just apply Crefeld algebra. So yeah, as you know, Crefeld algebra. So we need to. You have to do GB. You apply this one, you get this one. Likewise, if you apply this one, this is equal to 2p prime mu u bar p. Okay. So applying Crefeld algebra. Okay. Maybe I should write down like this way. U bar p prime times 2 times p prime mu. Then you can simplify. You can simplify it. I is equal to u bar of p prime gamma 0 p prime and p u of p. So So we just factor out this common factor u bar gamma 0 u here, u here, and then u bar gamma 0 u here, and what's left is that the e times p prime mu k dot p prime minus p mu k dot p. Like this way. Like this way. Okay, so these two cancel with this denominator 2 here. Is it okay? These two coming from this group of algebra 2 here. Okay, group of algebra 2 here. And these 2 cancel with this denominator 2 here. 2 cancel with this here. And you have to be careful of relative sign. So one is get the minus sign, the other is doesn't have. They have a relative sign. Okay, so that's what we get. And now, so therefore, but what we are interested in, so this is the contribution coming from this diagram, these two diagrams. So what we are interested in is square method. So I call it M soft. And then if you do the calculation, what we have is that the so M0 square. M0 square means I call it this one is M0. I can easily see you guys are very tired at the end of the semester. M0 square, and then we have a product of this guy. Product of this guy. From this guy, I think I'm going to omit the detailed calculation and give the answer because everything written in the lecture note. Okay, so that's what we get. Good. So now we are going to use the following trick. Okay. So this M0 square means that there is no soft the photon emitting. So M0 means there's nothing. If there's no photon emission, then this is the amplitude. Okay, amplitude. So therefore, if you use the what we have learned the cross section the sigma is indeed equal to some delta function. I forgot. 2 pi square delta momentum conservation 4, and then initial, and then initial, and then anyway. So I think we just write down like this way. D sigma EP equals to E P prime plus photon gamma, okay, is equal to d sigma 0, which doesn't have any okay, and M soft. So this is the Lorentz invariant phase space. Okay, the Lorentz invariant phase space. Okay, now we would take the following following frame of reference. So as you did in the homework, so always once you have the expression for sigma in general Lorentz invariant expression like this way. So what we need to do is just take a frame of reference and then evaluate the cross section. That's what you did in the homework, in fact. And we did. So what we have is P prime is equal to E times P M gamma. Too many gamma, sorry. Beta, sorry. So this is the relativistic gamma. So relativity system, you have a gamma and beta, right? Special relativity, gamma beta. So this gamma is not the photon, not the gamma matrix. This is relativistic special relativity that appear in gamma. Sorry, what's the expression gamma? I already forgot. 1 minus b over c squared, whatever. You already knew it. So you are smarter than me, so it's okay. Can anybody write the expression gamma explicitly? Okay. Gamma is equal to what?
1 minus b squared.
Square root? Okay. And divided by c, right?
Yes.
Okay, good. Thank you very much. Thanks. Here, sorry, here beta and b are the same. So b, since I put c equal to 1, b and beta is the same, actually. Okay, b and beta is the same. Okay. That's it. And K is just K is photon. So N is just unit vector. So this is the primary reference I'm going to take. Okay. So then we can just write down. So this expression. So if you take this expression, in fact, I'm going to omit. So people are very tired of looking at the calculation. So I'm going to omit the detail. So if you plug in this frame of reference, so this can be written as follows. Important thing is that the energy dependence of E gamma appear. E gamma appear in denominator here only, and then what's left is only dependence of the electron vectors, electron momentum vectors, velocity vector, electron. So that if you plug that one into here and evaluate what the end up is, all the electron energy contributions, just factor out. That's most important part. Then, okay, so this lengthy calculation, which needs lots of energy to do, as you already experienced. And if you plug that one into here, what's left is so this expression becomes following. So here, so this one, if you use the spherical coordinate, it becomes E gamma squared d gamma divided by 2 pi cube to E gamma, and then d omega, and then E squared E gamma f beta and beta prime. So here, this Lorentz invariant phase space is this guy. So it's just spherical coordinate of the angular coordinate of this momentum space, where the E gamma can be treated as the radius of the radius, and the omega is the angular part. And then we just put the M soft expression here into here, and then we have this expression. So therefore, if you just so here, what we're interested in is omega part is sensitive about this f, and the dE part is sensitive about this prefactor. Therefore, you can just factorize the angular momentum dependence part and the radius part, or energy dependence part. So d sigma 0, d omega 4 pi f beta and beta prime. So this one, and then alpha divided by pi e gamma e gamma. So therefore, this part is the angular dependence part, and this part is the only energy dependence part. And now, so we're very, very close to the form like this way. So if you perform this integral, what we get is the following. So therefore, the sigma. So the sigma of the sigma. So if you integrate out, sigma is equal to sigma 0 times d omega 4 pi f beta and beta prime times. So here you just put the cutoff and E mean gamma alpha over pi d E gamma E gamma. Okay. So now here this is the angular dependence part. You just integrate over, and this is the energy dependence part. Okay. And we are interested in the process that we cannot measure. So we're interested in process in here. We cannot measure, which means that from 0 to energy of photon is 0 to E minimum. Okay? That we cannot measure. So we would like to evaluate contribution, which we cannot measure. Okay? Then, as you can easily see, this will give a log, right? This integral will give a log. So the comparing that part, now we are very close to what we want to see. So this is sigma 0, and I call it this one. Let's call this one is equal to GIR. Or maybe I call it IR. Okay, IR beta and the beta prime, and times alpha over 2 pi and log E minimum gamma divided by mu square, both square. I think I should write them square. So here, so mu is the IR cutoff. If you put the 0, it becomes divergent. If you put the divergent. So this is the IR cutoff I introduced as before. And then but mu eventually goes to 0. Okay? Mu goes to E minimum, and I intentionally put square, so therefore you have to introduce 1 over 2 here. Okay, 1 over 2 here. And this integral I call it IR. And if you compare with this expression, it's very similar. Okay, it's very similar. So if you take a difference between them, so if you add them up, and in fact, if you just evaluate, there's something fucked up to something strange. I'm very sorry. I think. Sorry. Can you check this? Is there a 2 appear here in the Pascal Schroeder? It's kind of the factor 2 is missing. I'm very sorry. supposed to there is no 2 here. In my lecture note there is 2. Did you check? Let me check now. Sorry. Yeah. It's the end of section 6, chapter 6. Point. There is a one. Sorry. There is a alpha to pi. Okay. Then where did I make a mistake? Where did I make a mistake? 8.23. Okay, I will find the factor mistake. So I think this accepting this is the okay and this is okay, and then well, we want to do the difference between them. I think I will check later. I think there's factor of 2 something strange in my lecture note. Sorry, I think. Sorry, I made some mistake somewhere. But in any case, so what we have is that if my lecture note, according to lecture note IR, so the homework is to perform this integral and show this is equal to this guy, up to factor of 2. Sorry, I think before I post the homework, I have to be careful about my computation. IR of Q squared. Okay, let me be honest. So I don't know, maybe factor of 2 appears, but forget about at this moment 1/2, and take a difference between this guy and then this guy. Then if you accept IR and FIR is the same, we can write down the sigma measure. So the sigma measure is that essentially what we have is plus. So this one, IR. So what we can measure is that this part is we cannot measure. We evaluate the part which we can not measure. Okay. So we need to just add this contribution to what we can measure. Okay. Then so therefore, if you take a difference between them, what we have is the sigma 0 minus alpha. Sorry, I think it's sigma measure. I couldn't use sigma 0 pi square FIR Q square log minus Q square minimum of gamma plus order. So essentially this log denominator and log mu square cancel with this log mu square here. Okay? If IRR is equal to what was it? FIR. Okay? Do you understand what I mean? So if you take a difference between, so if you add the map, because of the sign difference minus and this is plus, therefore denominator log mu square cancel with this log mu square, and the difference is q minus q square and the e mean square. Okay? So therefore, since we have measurement and the upper, lower limit e mean square, so we can just take a ratio, and therefore we can avoid diagonal divergence. So that's what we have to avoid to avoid IR divergence. So this is what we have, and then so be careful. My lecture note, there are lots of some subtle point. I mean, lecture note I didn't have a 2 here, so but sorry. So this is question mark. It seems like my lecture note make some mistake and fucked up too. I will correct later. Okay, and in particular, so if you just do the homework is just show this one, show this identity, but I will be careful about the fucked up too. Sorry. And if you take the FIR, Q square goes to 0, limit, minus, so minus. If this Q square is very big, if Q square is very big, then this term becomes dominant. Therefore, if you perform this integral dx Q square and this is equal to log again minus Q square minus M square. So therefore, if you use this one, this expression, plug this expression into here, what we have is that does anybody identify where's this factor of 2 problem up here in the lecture note? Okay, you don't know. I'll check later. It would be nice some brilliant students can identify where's the factor of 2 problem up here. 1 minus alpha over pi or 2 pi becomes log minus Q square M square, and then log minus Q square E mean square M square plus all the first square. And this double log is called, there is a name, so called Sudakov double logarithm. This one is called Sudakov. Clearly, can you see the nationality from the name? Russian. Okay, good. Sudakov's double logarithm. This is called Sudakov double logarithm. Okay. Yeah. Now, I think around that time still the I would say Cold War, but during the Cold War, Soviet Union's the physics and math, theoretical physics and math is wonderful. As you know, Landau is a brilliant theoretical physicist, and then also anyway, so there are lots of contribution from Russian. Okay, so that's how you avoid IR divergence. So what we did is essentially we just need to add the contribution from Bremsstrahlung, which we cannot measure, okay, to the diagram here. Then we can avoid IR divergence. Okay. And the question goes on. So here we evaluate only one photon. What if you have a multiple photons? Let me erase here. Which one I can? Maybe I can erase here. So I'm not gonna do the calculation, but the detail is written in classical Schroeder. So I just give you a rough start. So you can have this kind of diagram. So you have a photon emitting two photons like this way, or you can have this kind of diagram. So you have a two photon emitting soft brown stripe. And we can do the same exercise what we have done. But this exercise can be done very easily. And this is indeed equal to minus sorry, I think there are lots of ambiguity in factor of 2. I'm very sorry. So factor of 2, my lecture note is very subtle. So this is, to be honest, question mark. My lecture note has there no 2 here, but let's include at this moment. Square and then FIR square of Q square and log minus Q square, E square, minimum, and so on. Plus order of Q. So if you include this one, what we have is just this part square. So this part square, essentially what we have. So therefore, at the end of the day, so if you include all the photons, so the diagram, what should I P sigma measured EP goes to EP prime plus multiple photons n gamma of n gamma, and sum of n is equal to 0 to infinity is indeed sigma 0 times exponential minus alpha over 2 pi. I'm very sorry, I'm very feel weird because of the factor of 2. Sorry, my lecture may be totally wrong about this factor of 2. Sorry. That I apologize beforehand. Like this one. Like this way. I think, strictly speaking, no, there's no square. So this means that this should be square. And I'm very sorry, this should be square. So therefore, this is equal to, so you just do the 10 expansion of exponential. Leading order is this guy, leading order is this guy, and the second order is this guy. And if you divide the third order, you get the exponential. So I mean, I'm just doing this one. E to the x is equal to 1 plus x squared over 2 plus x cubed is 3 factorial, and so on. So this each x is this guy. So if you do the evaluation of this Brem-Schrank with n photon, you just look at the Taylor expansion e to the x in the nth order. And what we have is sigma of 0 times minus q squared divided by mean square and minus alpha over 2 pi FIR and q squared. Okay, so that's the evaluation for Brem-Schrank. So that's the. So these detailed calculations are written in the Peskin Schroeder, Peskin and Schroeder section 6 point, the end of section 6. End of. So I'm going to omit the calculation. Any question at this moment? That's, I'm very sorry, the factor of 2 is maybe wrong. Factor of 2 may be wrong here. Sorry. There are lots of mistakes. Factor of 2 is question mark. And I will correct and send a WeChat message later. And also I made a mistake in the previous lecture. As I mentioned, alpha is equal to e squared divided by 4 pi. And in previous lecture I put the 2 square here, but this is totally wrong. E squared 4 pi. So as you can easily see, I often tell you lies, so be careful. Okay, be careful. I made a lot of mistakes and told you lots of lies to you, so be careful about when you read a lecture note. So this is the case. This is okay. So if you take a note, be careful. So the correct your note here. Correct your note. I'm very sorry, but this find structure constant. So yeah, don't trust me so much. I often make a mistake and tell you lies, so you have to be careful about when you take a lecture. Okay. Let's take a break, and then I will play the Hans Bethes interview after the break. Yeah. 10 minutes break.
I think the diagram now.
Which one? Which kind of diagram do you mean?
I mean the virtual fraction. Not for.
Of course. Yeah. That's right. You're right.
It seems that has been called, it wasn't the factor of 2 called.
The factor of 2 problem.
So,
So where did I make a mistake of factor of 2?
I saw that it came from we take the modulus square when we already know the vertex function. Okay.
I think what we are
So the vertex function is correct. So
I mean here 1/2, right? What is 1/2 of it?
when we evaluate the sigma, so we take the modulus squared.
I see.
So there is two here.
I see.
So it makes sense. When we talk about cross sections, there are no factor of 2.
Thank you very much. Okay, then after watching Bethes, so I'm not gonna erase my blackboard. And then I will let you know what the. Thank you very much. You're very helpful. Thank you. This one? No, I have a better answer to your question. You asked this one, right? Last time. I have a better answer, so I'll answer at the end of the lecture. After the lecture. And then I like to go to restroom.
但后面突然变成sigma，到3，然后有 modulus square， modulus square 小于
Makes sense. 我要问后面个2哪？modulus square， and the vertex function修正英文
Okay, so display. Can you help me to how do you show this one? My laptop? Yes. Epsilon. But I put epsilon 0 to be 1. Epsilon 0 to be 1. Yeah. Epsilon 0 to be 1. Yeah. Ayo. How do you show? Sorry, does anybody know how to show my laptop to here? Can anybody help me? Is it like this way? I hope. Wonderful, thank you very much. And what I want to do is that this one. I don't need a. Let's put. Oh gosh. How can I put the Tencent to the right screen? Okay, good. Oops, sorry. And then, oh my goodness. Okay, anyway, so. And then probably I should switch mode. Is it better? And then. Is it better? Okay, and Bede, do you know which nationality Bede originally? Hans Bede. He's German, and he's at this point is very old. He's the way he speaks is very. It's hard to. I mean, non-native speaker, it's hard to listen. So I just give you the transcript of this via WeChat. Okay. Oh, sorry. No. First, I just want to play this Shelter's Island. Okay. So this is okay. So let me give you the this one's the Shelters Island one. Okay, let's pray. Hopefully you can listen.
The Shelter Island Conference in the summer of 1947 was outstanding. It was unique. I've never
Can you hear?
before or after attended any conference which was so influential. It brought together a lot of the leading theoretical physicists
You
of
cannot
the
listen.
United States.
Is there any way to amplify the volume? Let's see. I use the maximal technique to Is there any way to make the voice louder? I don't know how to. Okay, let's.
The Shelter Island Conference in the summer of 1947 was outstanding. It was unique. I've never before or after attended any conference which was so influential. It brought together a lot of the leading theoretical physicists of the United States. It included Oppenheimer and Weizkopf and me, and also included Linus Pauling. It included younger people like Feynman and Pais, and I don't think I could name all the people. It also included a number of experimenters, for instance, Rabi and a group around him. It included a very important foreign theorist, Kramers, who had thought a lot about electrodynamics, quantum electrodynamics during the war. Kramers told us that we really had misunderstood the self-energy of the electron. He told us that after all, a free electron has a self-energy interacting with its own electric field, and that self-energy is included when we measure the mass of the electron. And therefore, that self-energy which a free electron has is already included. One shouldn't include it once more by calculating it. So never mind that it gives an infinite answer. You just disregard the self-energy of the free electron. You have to consider the difference in free energy between a free energy and, let's say, an electron bound in the hydrogen atom. And only that difference was what counted.
So did you roughly listen? The last one is most important.
Another great influence was
roughly understand. So at the end of the bed is the interview. So he talked about this Shelters Island conference. So it was for him so influential, and at the end of the day, the electron bonding, that only the difference was what counted. So that's the most important part. Okay. So anyway, this is Bede's interview. Maybe we can continue lump shift, or is any better how to make the acoustic or audio much better? Louder? Do you know how to do that? Okay, maybe should we go to different website? Web of Story. I think Web of Story. Is it better? This website better? Let me try. Yeah, I think sounds better. And then I just want to go to the lam shift part. I think it's a long interview, so I don't remember Shelters Island. Oh yeah, here you go. Let me try. This one is better or not?
Another great influence was
Maybe it's a bit louder here. Okay, there's a transcript here. Maybe I just also can send it to you. Okay.
Willis Lamb, who had done experiments using the newly developed microwave technique. He had done experiments on excited states of hydrogen, in particular the first excited state of principal quantum number 2. According to Dirac's theory, each should have a fine structure consisting of 2 levels, one involving an s electron, one having a total spin of 1/2 and the other having a spin of 3/2. And Dirac's theory gave us the exact formula for this, the separation of these 2 states. So Lamb was able to verify that by microwaves, but he found in addition that there were really 3 states, not 2. That there were 2 states of spin 1/2, one having orbital momentum 0 and the other orbital momentum 1, called in spectroscopy an S state and a P state. According to Dirac's theory, they should coincide, but they didn't. And Lamb not only showed us that they didn't, but he also measured how much they differed in energy. They differed by about an energy corresponding to a frequency of 1,000 megahertz, that is 1,000 million cycles per second. And that is known as the Lamb shift. Now, there had been vague inklings of that in spectroscopy before, but the resolution of optical spectroscopy was not good enough to make sure. And Lamb's experiment made it perfectly clear that these were 2 completely separate states, that one was an S state and one a P state.
So that was the Shelters Island, and Bete will recall at the next. Let's go to the next, and then let's finish. So on the way back to from the Shelters Island, he starts calculating on a train of this Lamb shift. And let's go to transcript, and hopefully you can see that.
the combination of these two talks, that by Kramers and that by Lam.
Maybe I should send a transcript to the WeChat before starting everything. I think that's it, right? If you cannot see, I mean, you just look at the. Okay, let's go back. And
Two talks, that by Kramers and that by Lam, stimulated me greatly, and I said to myself, well, let's try to calculate that Lam shift. Let's try to calculate the difference between the self-energy of a free electron and that of an electron bound in hydrogen in the n equal 2 state.
And when you said that to yourself, this was still at the conference.
This was still at the conference. I said to myself, I can do that. And indeed, once the conference was over, I traveled to Schenectady to the General Electric Research Lab. And on the train, I figured out how much that difference might be. I had to remember the interaction of electromagnetic quanta with electrons, and I wasn't sure about a factor of 2. So if I remembered correctly, I seemed to get just about the right energy separation of 1,000 megahertz. But I might be wrong by a factor of 2. So the first thing I did when I came to the library at General Electric was to look up Heitler's book on radiation theory, and I found that indeed I had remembered the number correctly, and that indeed I got 1,000 megahertz.
And this was describing the electron non-relativistically.
Yes, I was helped very much by a previous paper by Weisskopf, who had shown that in the Dirac pair theory, the self-energy of an electron, of a Dirac electron, only diverged logarithmically when you get to high energy. So I said to myself, once I take the difference between bound electron and free electron, the logarithmic divergence will probably disappear and it will converge. So let's just calculate the effect of quanta up to the energy electron mass times c square, velocity of light square, and let's hope that the relativistic correction won't make any difference.
okay, so that's what he says. I hope. I mean, audio is not good. Sorry, but I hope that you can understand what he said. Yeah. So maybe I can. I mean, of course, it's on the YouTube. But maybe this one you don't need a YouTube. Maybe if you were interested, you can watch again. I just send a link to. Good. And then, so what he mentioned is the difference is as you can easily see from here, electron. Yeah. So yeah, Dirac electron only double arithmetically, but once you take the difference, it converges. That's what we are doing, exactly what we are doing now. Okay, so that's about what Hans Bethe recall about Shelter's Island conference. And on the way back to his lab from the Shelter's Island conference, he did calculation of the lamp shift, and he got a right answer, non-relativistic. And that's what it's a quite amazing period that this kind of video is available to the public now. Maybe so including today, so we have a 4 lectures, so we watch 1 video. Last 3 lecture I will play some other video. I need to think about how the audio can be improved, but anyway, we'll see. Maybe next lecture I will play the maybe 5 months lecture or maybe Dyson's interview. I'll think about it, about the audience. So let me stop this one. I use lots of stuff. Okay, and now it should be okay. And thank you very much for this one. I will return later. Okay. Hans Bethe talk about the factor of 2 and the factor of 2. Correcting, I need to correct. So here, so factor of 2 about factor of 2. So here it's just about IM is equal to I gamma is equal to gamma mu f1 and plus I gamma sigma mu over 2m q nu f2. And when you do the computation, you have to square it. So n goes to m squared, you have to square it. So this is factor of 1 over 2 up here, but if you want to square it, so this will disappear. Sorry. So this will disappear, and this should show up. This should show up. 1/2 should show up. 1/2 it should disappear, and then all the 1/2 will be gone. Sorry. So as I mentioned, so the Bethe factor of 2 was a bit like a genius, like a Bethe factor of 2 is correct. My factor of 2 is wrong. Okay. Whereas I should correct. Yeah. So now all the factor of 1 over 2 I have written is wrong, and you have to erase in the lecture. Your note if you take it. Okay, so that's our divergence. Where's my lecture note? Where did I put my printout copy? Oh my goodness. Where's that? My printout copy is gone. Maybe evaporated. Just a moment. Unless I don't have it, I cannot give a lecture because I don't remember. Really? Or does anybody steal it? to boycott my lectures. Oh, seriously, disappeared. Oh, you found it.
No, this is a copy.
Copy? Oh, thank you very much. Somebody copied. But there must be somewhere, right? Where is your mother? Okay, maybe I will borrow. It's very strange. 非常奇怪。奇怪啊。 Did I bring restroom? That's quite If I bring it to restroom, I so much like my lecture notes. Okay. Anyway, I will borrow. Thank you very much. So line shift I talked about at the beginning of lecture, and then in the history of the anomalous magnetic moment and so on, I added some sentence about the concentrated correction in the lecture notes. So if you go to the section 1.2 or something, 1.3, I forgot. I add a bit more about line shift in the lecture note. Anyway, 非常奇怪的。Let's okay. Let's forget about it. So the Bennett talk about the self energy of electron. And what is self energy of electron? So I'm going to talk about self energy of electron. So self-energy electron is as follows. So as I mentioned, the electron receives lots of the quantum correction. I call it 1pi, which is something like this diagram, this kind of diagram. Okay. So, and 1pi means that you cannot separate. So therefore, you cannot have this kind of diagram. So if you have this diagram, so you can just separate to the two parts. So that is not called 1pi. This is not 1pi. Not 1pi. One particle irreducible. So this is called self-energy of electron. So it's kind of dressed by the photon propagating and so on. There are lots of the electron propagated can be dressed by quantum correction. That's called self-energy. And then, so one can just have the true quantum correction is just so when I call it this I sigma p. So this is the sum of 1pi contribution. Like this. Therefore, so therefore, this if you include this one, it's we know p slash minus n, I times n0, and then I times p slash minus n0, sigma of p slash, and then so I cancel. And then somehow I got a minus. Sorry. Then minus I times I over p slash minus n0 plus I p slash minus n0, and just a bit make a shorthand notation. Minus I times I will cancel to plus. So therefore we have sigma p slash p slash minus m0, sigma p slash over m0, and plus dot. We can have this kind of contribution. And then, so therefore, we have that so if you write down, so this one is indeed 1 over p slash n minus sigma p slash times pi. As you can easily see. Do you understand from this step, this step? So 1 minus x is equal to 1 plus x squared plus x cubed plus dot, right? So therefore, here x is equal to sigma over p slash m0, and there's the overall factor of I over p slash m0. You understand? Is it okay? Okay. So therefore, if you include the dressed by quantum correction electron, so therefore, sorry, m0. The position of Paul will be shifted by sigma of p slash is equal to 0 when p slash is equal to m. So m is no longer m0. Okay? So m0 is the mass of bare Lagrangian, but if you include all the quantum correction dressed electron, dressed means the dressed by quantum correction. Anyway, so dressed means is dressed by this photon propagator. So then the position of Paul will be of the propagator will be shifted by sigma. Okay? So therefore, bare mass and the physical mass will be different. That's the case. And also, as I mentioned. So here we can just write down I of Z2 divided by P slash minus M0, and Z2 can be understood. So from this step to this step, first we just factor out the P slash minus M times 1 minus divided by 1, okay? Divided by I. The I over this one. So here, we know the position of Paul is actually P slash equal to M, not M0. And if you take the Taylor expansion, the next order is the derivative of sigma. Okay? 1 minus sigma. So therefore, this can be treated as 1 over Z2. So this part is 1 over Z2, so therefore this is equal to this and this one. So therefore Z2 can be understood as the 1 minus the sigma, the P slash divided by when the P slash is equal to M. So inverse, okay? Z2 inverse. So that's the what we have. So the important lesson is that if you include the self-energy of electron, which is the rest electron, so the position of Paul will be modified. The position of Paul will be modified, and then also there is some residue is no longer 1 or I or whatever, simple I. So you have to be careful about the shift. So therefore, we are going to do is that we evaluate this sigma at one loop, and then see how this M will be shifted, and then the Z2. That's what we will evaluate Z2. So that's what we are going to do. Okay. Oh my goodness. The one you printed out is the old version, so all the calculations missing. Okay, it's I really need a. Why it disappear? Anyway, it's oh, sorry. Thank you very much. Thank you very much. Okay, so I think I put the lecture note here, and then somebody submit the homework later. I'm relieved. Okay, now I can continue the rest of the 15 minutes of the lecture. Okay, so that's what we have. So therefore, from here, as you can easily see, so the difference between M minus M0, which is, I call it delta M, is sigma of P slash, where P slash is equal to around M. Okay, so that's the difference between bare and physical mass. Delta M is equal to M minus M0. So now, so what we're going to do is we evaluate this sigma at one loop, which means that I call it minus I So we evaluate. So this 2 means that we have a 2. I mean, how is it 2? 2 in A. This 2 is just the one root. 2 and maybe 4 becomes 2 root and so on. But anyway, so it's just name. Sigma 2 is just a all one PI diagram, just sum of all one PI diagram. Sigma 2 is just only I consider this one loop diagram. Just evaluating this one loop diagram and plug this machinery, plug sigma 2 in this machinery, we will see, we evaluate the one loop correction to Z2 and then delta M. That's what we are going to do. And as I mentioned, as the beta mentions, the self-energy, so he also tried to calculate self-energy of an electron in non-relativistic limit after the Shelter's compressed. But as he mentioned, the important thing is that the difference. So the difference means that we need to push the infinity to the counter term delta 2. And this delta M is really the difference between energy. So we will see that the M0 and delta M, is that if you take a difference, you get the M. So that's what the beta mentioned. Okay. So now, so we just apply the final rule. So here minus IE square coming from this 2 point. This 2 point will give you minus IE square. And then there's a momentum integral over, sorry, I think there's a typo in the lecture note. There's a force. And then we have the gamma mu. Okay. I mean, maybe I should write down like this way. K square minus M2 square I K slash. Oh my goodness, what am I doing here? It's a very strange. There must be K slash plus M0. Sorry. There are lots of mistakes in the lecture note. So IE gamma mu P minus K square minus mu square divided by minus I. So this is the propagator. I think the lecture note I made a mistake in there's no slash in the lecture note. Let me check. Did I correct? No. I'm very sorry. I think I made a huge mistake. So the K slash is missing, and I just get rid of it. This one. So minus IE gamma coming from here, and minus IE gamma coming from here. More precisely, I mean, you can just write down like a G nu, but here you put the G mu nu. So this is the correct diagram, and the K. Okay, then let's write down the usual. I think you already get used to it, but let me. So this one is equal to the propagator of the electron, and then this one is equal to this corresponds to the photon propagator, and of course this vertex corresponds to this point and this point. Unfortunately, green and yellow you cannot distinguish from the black. Okay. And again, so we use crippled algebra to massage this propagator. So I just introduce IR cutoff mu square for photon propagator. So this is just IR cutoff. Okay. And then what you end up is the following: d4k. I mean, I'm not going to repeat the calculation everything. So because I don't want to make you bored, I'm going to omit all the plus I epsilon divided by, so the denominator coming from here, and the numerator, you need to do a little bit massage. Essentially what we have is gamma mu k slash plus m0 plus gamma mu, but this one can be, you use the crippled algebra here, and what we end up with the, okay, there are lots of typo in this lecture, sorry. What you end up with the only here, after doing the applying crippled algebra, sorry, like this way, m0. So this is it. And now again we will do the standard method of the Feynman parameter and so on. As I mentioned last time, so I'm going to erase maybe this part. Okay, maybe I can erase. Okay. So again, so we will introduce Feynman parameters. So as I mentioned, this A1, A2 is equal to dx dy delta x plus y minus 1 over ax plus 2y square. That's the Feynman parameter we will introduce. We will do the same thing for this A1 is this guy, A2 is this guy. That's what we're going to do. I think it must be 2 here, as far as I recall. Am I correct? N minus 1. Okay, let me check. I'm very sorry. My memory is so weak. 1. Okay, good. N factorial. I think N minus 1 is maybe 1. And then if you introduce that, so minus I sigma 2 of P is equal to E square and D4K. I mean, you guys need to familiar with this kind of computation. And then what we have is that the K slash minus 2m0. And you just expand. So you just multiply x times this guy plus y times this guy and expand this guy. And then what we have is that the x plus y k square minus 2xk dot y m0 square plus xp square minus x mu square. And then total square in the denominator. Okay, then we can just, okay, actually, there are lots of typo in the lecture, I think, no, it's okay, it's, I think it's okay. I think it's okay. Okay, again, so now, so what we will do is the following. So that we can just write down E2 square, and then dx 0, 1 dx, and then I think, yeah, I think I should write down the next step. You can take a look at the lecture note. I think k slash minus 2m0 and divided by k minus xp square minus 1 minus x. So this is the, you have to do the calculation. I mean, you have to get used to it. And then unfortunately, or fortunately, or whatever, it'll appear in the final exam. This final parameter. This calculation final parameter will show up in it. So you just massage this one into here. You can get the perform y integral, and massage inside. You can bring it this one. And now, as you can see, what we are going to do is just call this one is L. This one I call it L. Okay. And then the rest of the part I call it mu. This part I call it mu. What we are going to do is that I call it this is plus and just overall bracket, and I call it equal delta mu as before. Okay, that's what we did last time in the evaluating this anomalous magnetic moment. Okay. And then apply the Pauli-Wheeler's method. So if you apply this, so if you call this is L, and this is called mu, and the numerator becomes, hopefully my type will last here. So this one will becomes L slash plus xp slash minus 2m0. Okay? So this is the numerator. Is it okay? So I call it k minus xp is equal to L. So therefore k is equal to L plus xp. And you just slash it. But now we know that the dl, we do the same thing. So this one is equal to what? This integral. This is integral is 0, right? Is it okay? Because I mean, it's an odd function. So L goes to minus L. It should be equal to the same thing. So therefore, it's odd integral, so that it becomes 0. So we can ignore this one. Okay. So therefore, minus I sigma 2 at the end of the day. So we have minus 2e square dx is 2m0 minus xp slash. I don't know why so minus times this one is equal to this one. And then what's left is the dl integral to the force. And you just apply the Pauli-Wheeler regularization. Okay? We will do the same Pauli-Wheeler regularization. We already experienced that. So Pauli. So here, as I explained, so this has a this has a log divergence. But we can just do the replace. This is the dOL to pi force 1 over L square minus delta mu minus 1 over L square minus delta lambda square. Okay, and a perform integral. So this is regularization. So this can be understood as you have like a heavy photon propagator. You have a heavy photon propagator to regulate the integral. to write this integral. And then you need to perform this integral. So angular moment, sorry. And also the last time I told you wrong, so I mean it's square, the volume of 3 sphere is d omega is equal to 2 pi square. Sorry, last time I called it 4 pi square, but that's wrong. And if you perform the angular integral, what you get is, of course you have to perform weak rotation. Okay, so from here to here, to perform weak rotation, excuse me, weak rotation. Okay. Does anybody turn on the air conditioning? Oh, is it here? Anyway, rotation. And then write down angular spherical coordinate. Then at the end of the day, what you have is the anyway, so this kind of stuff you have to get used to. But anyway, so in the you have to get used to it. I think can you turn off the air conditioner at the back? I think you can switch off. Can you? Anyway, you cannot understand what I said. I'm over 4 pi square. Sorry, square. 4 pi. Thank you very much. Log. Okay, now this is exactly what the Weiner mentions. Do you understand? So Weiner mentioned he evaluates self-energy of electrons. Okay, and then he got a log divergence. This is, but he did the non-relativist calculation instead of relativist. We are doing a relativist calculation, but he did non-relativist. But he knew he has a log divergence at the even 1947. That's why, yeah. Anyway, so log divergence. Okay. Oh, did I put the M0 everywhere? Okay, good. I put the M0 everywhere. And where should I erase? I think I should erase here. Good. Anyway, so what I'm doing here. Okay. So now also we will take lambda goes to infinity. Lambda goes to infinity. Is it because? Sorry. When you take a lambda goes to infinity, this sigma 2 of p can be written as follows. So alpha over 2 pi, and sorry, this integral, we plug that one to here, and then if you take lambda goes to infinity, what matter is only this term. So delta mu is this one, and delta lambda is just replace mu by lambda. Okay. And then when lambda goes to infinity, only this term matters. Okay, in the numerator, in the log. So therefore, what we have is that the from 0 to 1, the x minus x p slash log x lambda square 1 minus x m0 minus square minus xp square plus x mu square. Okay, that's the case. Okay. So now, first we'll take a look at the difference of the physical mass and then the bare mass. We can just take a look at it. So as I mentioned, delta m is equal to m minus m0, and this is the at the order alpha, it's just sigma 2 of p is equal to p slash is equal p is equal to p slash is equal to m, and roughly speaking, okay. So therefore we just plug in the and then this is roughly speaking sigma 2 p slash. So the first order, so in first order we just set m p slash equal to m0. Therefore, if you put the m0 here, so you just plug in this is m0, and this is equal to m squared, m0 squared. So you can factor out that the integral over 1, you have a 1 minus x squared here, and x, and if you take the integral over it, so what you get is that this is equal to 3 alpha divided by 4 pi and 0. And then you just perform the x integral, and what you get is log of lambda squared and 0 squared. So you just perform the dx integral once you plug in p slash, or p is equal to m0, p squared is equal to m0. And what you get is this numerical factor, which is not that important. But the important thing is that the difference between bare mass and the physical mass has this kind of contribution. So therefore, what we have is that so m0 in physics is equal to m0 1 plus 3 alpha divided by 4 pi lambda squared. I mean, okay, look, ln, just natural log lambda square and 0 plus order alpha square. So that's so that's the relation between physical mass and the bare mass. And we know this is about this is about 155 keV. 155 in our scale, in our low energy scale, this is 155 keV. But here you have a log divergence, okay? Log divergence. So therefore, to get m is 500 roughly keV at our scale, at the high energy of bare mass should be very, very small. Okay? Very small mass times very big, so that it should be tuned to 511. That's what it means. So m0 is a mass at the order scale lambda. Okay, the energy scale lambda. But this has to be very small, so that if you multiply the log lambda square, you get the 500 keV in our scale. So this means that most of the electron mass, so this is really close to 0. It has to be close to 0. Okay? If you go to high energy, the electron is really massless. Should be massless. if you measure. So this means that if you include, all the mass of the electron in our energy scale is that most of them coming from self-energy. All those quantum correction, if you include this one, the electron mass itself at the high energy should be negligible, or it should be almost massless. But if you include all those quantum corrections, self-energy, that will give you mass of electron in our scale. Okay? In our scale, in our energy scale, the mass of electron is all come from self-energy interaction between electromagnetic field and the electron itself, and then all the quantum correction. That's what it means. Do you understand it? Okay. And the important thing is that, of course, this part is the positive. This part is positive, which means that all the self-energy contribution is positive. Okay? So those the self-energy, whatever, dressed, the electron dressed. So which means that it's kind of like, okay, if you use a metaphor. Metaphor is that if you use a metaphor as a human being, it's a kind of electron spin. Electrons are almost very, very, very super light. But if you dress that with the electromagnetic interaction, it becomes very heavy. So which means the electron's cross is super heavy, 500 keV, even though his weight is almost negligible, 0. That's what it means. Do you understand? Yeah. So if you go to the high energy, you can ignore this kind of if you go to high energy and measure the electron at the high energy, really high energy, so you can just see the naked electron, okay, which is almost massless. Okay, let me move on. 20 minutes has left. So now we are going to evaluate Z2. So Z2 is just derivative of this one. Okay, so what we need to do is just take a derivative of this guy. Okay, I'm going to erase this part. Okay, so now let's try to evaluate Z2 here. To try to evaluate Z2 here, we need to take a derivative of this sigma 2. Okay, and then let's do that. So sigma 2 is over there, and then what we need to do is the following. Gamma mu inverse 0, 1 dx derivative of T mu. Okay. Of the one over there. So to take a derivative, so I think I just swap denominator and denominator and numerator and put the minus sign here. Which means that the 2m0 minus x gamma mu okay, so this is okay. So I just swap a numerator and denominator, so the output we have a minus sign here. Okay, and then now I just apply derivative partial mu, p mu, and then since we have a slash, I have multiply gamma mu inverse. Okay. Okay, let's do this calculation. It's just simple. I mean, you just need to do this kind of calculation. Unfortunately or fortunately, I mean, this is the. Unfortunately, listening. Yeah, QFT. Anyway. For instance, Schwinger and Tomonaga did way more involved computation. We are very lucky to all the formulation are more or less developed, so that even though this calculation looks complicated, but it's much easier than what the Schwinger and Tomonaga did. So that's a kind of the word of relief to you guys. So the first one is just derivative of this guy. First one derivative of this guy, and second one derivative, second time derivative of this guy. Yeah. And then minus 2x minus x divided by x lambda. So the first, as I mentioned, so first time derivative, this derivative acts on p. The second one, this derivative acts on p squared. Okay. Now we again need to put the, so here, as I mentioned, p slash is equal to m0. But at the order, the first order, we just put the m equal to m0 like we did in here. So the first order approximation, the m can be put to m0. So that here we should put p slash is equal to m0. The first order, p slash equal to m0, and p slash equal to m0. Okay, that's what we need to do. Okay. Now plug that one to here. P slash this is m0 square, so we just have 1 minus x square. And then the second part is the, let's see, p slash is m0. Okay. Sorry, I think I made some mistake. Did I make some mistake or not? It's okay. It's okay. Okay, so this gamma mu inverse cancel with gamma mu here. And also here gamma mu inverse time p slash, you get the m0. So that what we have is at the point. Should I write it downstairs? Okay. I hope. So this is equal to alpha over 2 pi. 0 to 1 is x. So 1 minus x square coming from, so that you have to factor out m0 square. So m0 square plus x mu square divided by x lambda square. This is the first term. Minus x square m0 square. So this is really coming from here. And 1 minus x square is the p square is equal to m0 square plus x mu square. And I'm very sorry, I think lambda square missing. So as you can easily see, this term cancel with this term. And then, what am I doing here? Yeah, there's an overall factor, m0 square will appear here. And then we need to multiply gamma mu square here. This will give you, let me think, just a moment. So 2m0 square should come from this m0 square and m0 here. And 2 minus x coming from here. And 1 minus x coming here. X, am I missing x? Yeah, I mix x. Here. That's the case. And then what we need to be careful about this one. Minus mu inverse p mu. I think. And how should I take this gamma mu inverse? I think I should use Crufel algebra, right? Let's see. Gamma mu and gamma mu is equal to what? 1? No, I think it should be 1, right? Okay, it should be 1. So therefore, it's just gamma mu. So therefore, this is gamma mu times p mu will give you m0. Okay, fine. Fine. So this is the case. Okay. So now I evaluate it. So as I mentioned, so what was it here? So we use this one to evaluate z2 inverse. Okay. And then, as I mentioned, z2 is 1 plus delta 2. And then, so therefore, z2 inverse is equal to 1 minus delta 2 plus, of course, in alpha is very small. So the order alpha. So this is the order alpha. I mean, you just do the tail expansion, the inverse, and of course it has a delta 2 alpha square and so on, and so on. So therefore, the order alpha, we can just identify this one. Identify order alpha. This can be identified delta 2 of alpha. Okay. Did I write the sign correctly? I hope. Yeah, I'm right. Okay, so this is the second version. So therefore, so as I mentioned, so here, what we need to do is you have a bare Dirac field, bare, and to get the physical Dirac field, you have to normalize like this way, physical, renormalize, so physical. And we evaluate delta z2 by taking derivative of sigma 2. Okay, that's what we did. The story does not end, in fact. We evaluated the z1 is equal to 1 plus delta 1 by using this one. This one, so we just set this one is gamma mu z1 p prime p is equal to gamma mu limit p prime goes to p. That's how we define gamma z1, in fact. And evaluating this one, we evaluated z1. This coming from this delta 1 coming from is equal to delta f1 z. That's what we did. And try to compare. Yeah, I'm pretty sure you already put the expression delta f1. And but if you try to compare delta f1, delta 1 and delta 2, the expression is very similar. Let me erase. Let me rewrite F1 again. Fortunately, I have 10 minutes to finish this section. Good. Unfortunately, I didn't print out this part, so that I need to go back my lecture note and then rewrite it again. Okay. Sorry, this is minus. Sorry. Delta F1 is equal to minus delta. And then where was it written? Oh my goodness, I forgot the word I have written. Oh yeah, it's no longer z. Maybe I have written x, right? So maybe I should write down the x for it. I think it's the same as before. Okay, I think I should write a minus alpha. So, minus alpha over 2 pi, and then the rest is the same. X lambda squared. It's a magical same. And 0. X mu squared. And the minus sign here? There's no minus sign. Good. Plus 1 minus 4x minus x squared divided by 1 minus x x mu squared, and there is some numerical factor m0 squared. Remarkably similar. Remarkably similar. Minus alpha over 2 pi. Okay. And then we just apply the following integral parts of the just a moment. I think I made a mistake. Yeah, there's no x. Sorry. I hope now it's okay. I didn't print out this part, so unfortunately I have to go to back. Yeah, now it's okay. And now, so we know that the so 0, 1, the x 1 minus 2z 2x, which means that the 2x, which means the difference between this guy and this guy. Okay. Unfortunately, here's also I have a mistake. There must be x here, show up here. Yeah, x up here. Sorry. Yeah. So x times ln, and this guy. And if you take a difference between this and then this one, you get the 1 minus 2x. And ln. If you perform this integral, what we have is minus 0, 1 dz. Sorry, my language is x now. 2, 1 minus x, and 0 square, and square. I think. Yeah, I mean, okay, I think I should write down the following expression. At the end of the day, so what we get is the following. And this. So if you use this one and then compare, plug that one into here, you can show that this, if you use this integral parts, you can just show that delta 1 is indeed equal to, it's not similar, it's indeed equal. Which is quite remarkable. So let's see, how can I, sorry, what I'm doing here, so here, so let's see, let's compare between them. Sorry, just a moment. Here, if you compute this one, but I have a few minutes. Anyway, so let's first finish the story. So if you plug this one into here and then just manipulate, you can just show that the rest of the part is equal to this one. And if I think that dx times 1 minus x, if you integrate this one, you just get 0. Are you sure? No, 1. ddx 1 minus x is what? 0, 1. It should be x minus 2 minus x squared, is it correct? And 0, 1 is equal to what? 1/2, and is it 1/2? Is it correct? Okay, so 1/2. So therefore, I think you have to do the calculation, honest calculation. It's a 1/2 coming from here, and you have to use the calculation. Just if you combine this one and this one, and you get that one. So you have to do the calculation. And one can show delta 1 is equal to delta 2, in fact. And which is quite remarkable. Delta 1 already coming from this diagram. And delta 2 coming from this diagram. Okay? But however, at the end of the manipulation, one can show delta 1 is equal to delta 2. So this means that the Z1 is equal to Z2. It's a miraculous coincidence. But in fact, so at the end of the lecture, the final lecture, we will show that this is indeed a consequence of so-called Ward-Takahashi identity. Ward-Takahashi identity is a quantum version of Noether theorem. So it's coming from symmetry. So quantum version of Noether theorem predicts Z1 should be equal to Z2. That I'm going to explain at the final lecture of this semester. So yeah, let's stop here. And this calculation, I'll leave it an exercise. The show delta 1 is equal to delta 2. I did it once, but I already forgot. When I prepared the lecture, I already did it once, but this was a few weeks ago, or like 2 weeks ago or something. But I just leave it as exercise. So what we did is that finally we calculate Z1, Z2, and then delta M. So we calculate delta, so what's left is Z3. What's left is Z3. Okay, yeah, it's a good time to stop here, and then next time I will talk about so-called Shannon. Okay, so this next section I wrote like this, right? Lemon. He's actually Swedish. It's a pronunciation Shannon. Okay, he's Swedish. I met his actual grandson was also a physicist, working on string theory. I met his grandson actually, and he explained to me the correct explanation, correct pronunciation, his family name. So we talk about Shannon and also LSD. Let's stop here.
Here you see that this